Still morning? Yes, good morning. I'm Nick Napoli. I work for the Northeast Regional Ocean Council and the Mid-Atlantic Regional Council in the Ocean, and the Regional Wildlife Science Collaborative is part of all of that. Carl, please post those immediately. I want to prove to my wife that I left Mother's Day for a meeting at the beach. Not that I'm going fishing with John and drinking beer. Okay, no, hide those pictures. Anyway, okay, so I actually asked to moderate this panel because for a few reasons. First, Jesse Cleary's tired of me, so he didn't want me to moderate his panel. But more importantly, about 15 years ago, before ocean planning, I was doing ocean planning, I was doing land use planning. About 15 plus years ago, I started working on a new thing called ocean planning. And when I started, there was not much geospatial data that were available. And that was shocking coming from a land use planner's perspective. And a lot of that's changed, thanks to most of the people in this room. And now we have many examples of the Marco portal being used in many different contexts: offshore wind, aquaculture siting, telecom cable siting, maritime safety, anchorage, siting of anchorages, port access route studies, a whole bunch of reasons, ways in which the portal is being used, and that's fantastic. And now we're looking at what is possibly the greatest data collection opportunity for the ocean that we've probably ever seen, with federal funding and offshore wind. We have great systems that need to improve, and data need to be shared. A bunch of the discussion about that. And research needs to be coordinated. And if data sharing and research coordination were happening already, I wouldn't have a job. I'm looking forward to you all retiring me. Until then, we have places, venues for this through Marco, through the Regional Wildlife Science Collaborative. And I was excited about this panel because Gwen's going to give an example of our data and use, and I'm curious to hear more about data and use in a construction operations plan and all the other data that goes into a construction operations plan. And because we have great partners in Rutgers. Working with Josh Kohut, Mike Crowley, it's fantastic. They're perfect examples of good partners for data sharing. And I think they're going to show us that through their presentations. No pressure. And they all tell me they're going over 15 minutes, by the way. Anyway, I'm done. Easy part over. I'd like to introduce Mike Crowley. What is your title? You've got several titles yourself.
Technical Director, Americas.
What other titles do you have?
That's good.
That's good? Okay. This is Mike Crowley. He's fantastic. He's going to tell us about a lot of things.
I'm here to talk about stuff. Let's see if this works. Give it a try. No? It's okay. I'll use this one. We're good. It's okay. I just turned it off. So, all right, Mike Crowley. Today I'm representing Maracus, Mid-Atlantic Regional Association Coastal Ocean Observing System. And I'm going to talk a lot about data that we acquire in Maracus. And what we do is not the marine spatial planning aspect like we've been seeing today and what Marco focuses on. Carl and I always tag team at different meetings. We deal with the real-time data. What's happening? What do you want to do? Are you going out tomorrow in a boat? What's happening offshore? What's the forecast? What's the marine forecast? What's the meteorological forecast? What's the data? What's the latest information? That is what our piece is. That is what our focus is. So that's what I want you to get out of this talk today. Is that's what Maracus does. We have a booth straight behind the wall over here. You can come visit us, and we'll give some demos of what I'm going to show today. So Maracus, what is it? So it's one of 12 groups around the country that's part of IOOS, the Integrated Ocean Observing System. IOOS is part of GOOS, the Global Ocean Observing System. So it's the U.S. piece of the Global Ocean Observing System, and then the U.S. is broken up into these 11 regional areas, and Maracus is Cape Cod to Cape Hatteras. That's our backyard. There are 17 federal agencies that make up IOOS, but NOAA is really they're the key piece. They're where their funding comes through. They're the ones that do a lot of the leverage. So what does Maricoo's do? Well, we gather data. And we are actually over a dozen partners. Maricoo's has a central office, but there are 12 partners, mostly academia, ranging from Woods Hole, UMass, Stony Brook, UConn, Rutgers, Monmouth, Delaware, Maryland, VIMS, Old Dominion, and then we have partners that do a lot of the data back end, which was RPS, which was just bought out by Tetra Tech in the last year. And they do a lot of the data, they put all the data together, and we're going to get to that in a little minute. So we do observations. We look at, we gather our own satellite data. We have HF radar that measures surface currents up to about 100 miles offshore. We get data from all sorts of different buoys and information there. We have gliders that go in the water and fly around and get different information about the ocean. I'll show you a little bit more about that. All this goes into models, right? We want to do forecasts. We want to be able to better predict what's going on in the ocean. And these models then lead to products, as do the data. So our 5 themes that Maricoo's focuses on are marine safety, fisheries, water quality, coastal hazards, and energy. So all the data is certified. So what does that mean? What it means is we went through a hell of a process that NOAA oversaw, that we had to go through and dictate out everything that we do for data processing, QA, QC processes up the wazoo. Several years ago, several months of work from all the different team members to go through quality control, data archiving, data sharing, metadata, and some more metadata to make sure everything has information backing it up. And why it matters? Well, it means that we're backed up by NOAA, right? If we put data out there, NOAA is basically saying it's as good as the data that NOAA puts out there, and I will say, and I think a lot of circumstances, it's actually got more QC applied to it, and it's slightly higher level than what NOAA puts out there. So, all familiar probably with that map on the left, the different regions, but just say that we do data collection, QA, QC, the sharing, the management, the decision tools is what I'm going to show you and focus on today, and that's Oceans Map. We get data from platforms of opportunity, a lot of federal sources as well. We integrate, and that's a big word. We're integrating lots of different real-time data sets in one spot, and the data that we acquire too all goes into one place, all these models. So Oceans Map, that's the tool. You see here a display of the East Coast with some buoy locations on it, sea surface temperature, ocean currents. We integrate, we're archiving, so that first bullet there on the right. It's a central location for different data streams to be all integrated together and visualized at once. There's a table of contents that allows you to search, look, see what's going on into forecasts. You can search and do filters. You can query the data. And you can plot, you can compare. There's the statistics up in the top left corner over here, looking at data statistics. You see RMS comparing models to real-time data. I'll show a little bit more about that. You see plots of data along the bottom at a given point, at a buoy point. And then for the super nerds out there, we allow direct access to the data. So all these different data sets have locations you can click on and go, I want to get that and do some analysis on that data, and you can go get that off the different servers. Whether or not we're serving the data or it's federal, we'll send you to those different spots. So this is the pretty view of the different data sets we get from satellites up top, boats, floating buoys, moorings, gliders, AUVs, different data sources that all gets put together. That's the pretty view. That's the table of contents, right? So there's over 125 different data layers. And I say, okay, is just a data layer. What is a data layer? Well, it could be a simple model or it could be a glider. It could be hundreds of buoys, each with 5 to 10 different variables. It could be a 3-dimensional model of ocean oxygen up and down through the Chesapeake Bay. There are a lot of different data sets. There's a lot of models listed here, a lot of federal assets for observation statements. Just trying to say there's a lot of information in this thing. So I'm going to talk about a couple of the tools quickly. Validation tool, simple view. We have a model of wave height. At the top right, you just see the color. Wave height's getting gradually higher offshore from the blues that are low levels. And we're going to compare to that little buoy. We're going to compare the model of this wave height that's what that is, to an actual buoy. And you see a line there in the bottom left corner with all the little green dots looking at a trend line to see how we match up. There's statistics to show you how well your model is actually comparing to your actual measurements. The bottom right is kind of the key plot with the blue line and the red line there. So the red line are actual measurements. From left to right, it's time. There's a couple days being plotted there. So you're seeing time. The straight line up and down, so right here, that was the point at which someone grabbed this data and looked at it. That's the current time. Anything to the right of that is a predicted model. So the blue line is what the model's predicting. Everything to the left is what the model did predict in blue, and the actual red lines are the actual data. In this case, it's wave height. So you can see how well, you can validate how well a model is doing in a given area. And there's a lot of models to look at. Some do better in certain situations, some do better in others. Now we take another step. If you're a wind developer, if you're a boater, you're going to go out in the ocean, and you want to know what's going on in the next few days or day, we have a wind developer's dashboard, as we call it. And you can do stoplight, red, green, and yellow, and you can define the terms. Like in here, in this case, on the bottom, define some terms. I'm going to go offshore. I care about winds. I care about wave heights. In this case, anything I'll put in green as my term, anything under 15 knots and 4 feet, I'm comfortable going out and operating in those circumstances. If it pops up yellow, it's, again, I've determined what these numbers are, between 15 knots and 20 knots, and waves are 4 to 6. Red, I don't want to go, right? That's winds higher than 20 knots and waves higher than 6 feet. So you see yellow up here in green. So yellow, it's kind of sketchy at this one point, this one little buoy that's off Block Island. And I also have a wind rose there to see what the wind directions are coming from. One key piece I haven't mentioned yet, there's a little icon that looks like a less than symbol far up in that right-hand corner. And then there's a link in the bottom left. Looks like a little hyperlink there. If you click that little less than symbol, you can generate a hyperlink and save this exact dashboard and send it to anybody you want to. It gets saved, so that is actually an active link. If you click that, you'll get that exact view, except you'll get it for today. Like you will see exactly what you want to see and share it with friends, except you're looking at today's data. So that was the stoplight at a point. This is stoplight on a very large area. Where could I go work? So again, my constraints, I've detailed what I want, what's acceptable as far as red, yellow, and green, as far as wave heights and winds. And this is what comes up at a given moment in time in the Mid-Atlantic. Now the bottom right gets more interesting. I know I've got to go out and do some activity for a few hours, say at a wind turbine, I'm going to go fishing for a few hours. What you see in the bottom right is time. You're seeing several days of time, and it's telling you about a day and a half from now, there's going to be a green window where you're comfortable with the winds and the waves. And maybe that's the time to go off at that point that you picked. But beyond that, things start getting a little more sketchy. So maybe you don't want to go out there and do any activities. Again, this can be saved, hyperlinked, and shared with somebody else so they can see exactly what you're looking at in time, and you can see the same forecast. Another tool, we call these little red dots in the plot there virtual buoys, except in this case, there's several of them in a transect. And over to the right, we're actually seeing time if you were in a boat going north to south. Along that transect, you're now seeing what water levels are to the right, the plot of water level and surface current directions. So you can get an idea as you're moving through time what's going to be happening as you're transiting, well, in this case through the bay, but heading toward offshore. So again, and there's that little less than symbol again, where you can click and again generate this exact view for somebody else to look at, or it's a view that you're going to use every week because you go out in the same transect every week and you save that information and you can see over where you're going, what's going to be going on, waves, winds, currents, anything like that. So we have a little bit of overload on all the different partners, and these are partners that either Maricuz has worked directly with or a lot of our partners. And I mentioned again, Maricuz is a group, it's a consortium of a lot of different teams put together. I'm actually out of Rutgers University, again, one of many different universities that are involved here. And at the bottom, of course, it's all the regional groups here. Up on top are some of the groups that Maricuz has worked more specifically with in some different situations. And I'm going to give a couple of examples. There's a lot of potential data science data that can be coming in over the coming years, like a lot. So a couple of examples of data that we've pulled into the oceans map. The Atlantic shores. This is a plot from a buoy, or we have several buoys that we had data from. This is a plot of one. We're looking at air temperature, and seawater temperature being plotted. And then we have a couple different groups that we work with. Now it's Empire and BP, I guess they're separated if I recall correctly. But we have a plot there from beacon wind of wind speed and wave heights. And these are just data sets. We work with them. We get the data. Well, sometimes we'll do our own QC on it too. We make sure that we're doing some checks again because our data's got to be certified. So it goes through checks and balances. So what's next? I've talked a lot about the physics. What about maybe a little biology? So on the left side, you see surface currents. That's from HF radar. We have those measurements every hour, surface currents that come in through the entire mid-Atlantic, and then you see little zoom-ins of the bays. Those are high-resolution surface currents, again, that come in every hour at the entrances to the bays. If you overlay them at a sea surface temperature image, like in the middle, you can see the currents matching up with the temperature, and then that explains a lot. You can see frontal boundaries and what's happening, convergence, divergence zone. Speaking of convergence and divergence, I stole this the animation from Josh. This is a plot using the HF radar looking at surface divergence and convergence in Antarctica. We set up CODARs in Antarctica at Rutgers, and we were looking at potential foraging areas for penguins. So if you can do that in Antarctica, you can certainly do it in Mid-Atlantic because we got loads of these systems up and down the Mid-Atlantic. We also have gliders, and Josh will be talking more about this later. We have numerous gliders that have a lot of different sensors on board. Look at zooplankton, all sorts of different things. In this case, we're plotting pH and oxygen and temperature from these underwater gliders. We had a bad event last summer. There was a stressor event for fish and lobsters. There was a die-off. Luckily, I forget which hurricane came close enough to shore to mix things up late in the season, and that ended that stress because it mixed the entire water column late in the season. But these gliders get all this pH, oxygen, phytoplankton data, right? And then we have friends like up at Woods Hole, Mark Baumgartner, that has on the left, you have whale detections for fin whales from a glider, and you also have matose data. I know matose is a little touchy as far as the data and the fish tracking data. But these are not integrated into Oceans Map yet, and that's something that we want to look into. Because if you can put it all together, on the left you have right whale detections from a glider, those little red dots on that track, so the glider is the track, that gray line, and there was a couple of right whale detections. Then we put it together with the glider data on the top, the two white bars, that's where those two right whales were detected on the edge of a thermal front offshore. Bottom center, the two detections are on the edge of a surface current change in the HF radar measurement. So there's some sort of frontal boundary there. And then to the right, Matt Oliver's data, Matt Oliver here at UDEL, we're looking at different water masses. And there's a water mass break right where those whales were. So if you could put all that together and integrate it into one system, that'd be awesome. So that's something, Mary's in the back here. She's my counterpart and she's heading up all the stakeholder engagement work, assistant director. If you can put all that together into one, and we want to do that, we'd like to do that with Oceans Map. We're going to try to get this data integrated. So boy, we just don't have that. We don't have the matose data. We don't have the whale data, but that's something that we're going to be working on the next year. So again, we're going to do some demos tomorrow of Oceans Map on the back, and we'll be here next couple days.
Thanks, Mike. I can't ask him questions yet. That's for later. Okay. All right. Next up is Gwen Lockhart from Tetra Tech.
Hi, my name's Gwen, and I'm an offshore GIS scientist. I work for Tetra Tech, which is an international consulting company. Right now, I want to switch gears a little bit, and because I represent a data consumer, and I want to take the opportunity to provide an overview of how an environmental consultant uses ocean spatial data projects to support offshore wind developers, and specifically how we use them in a construction operation plan. So I'm going to give an extremely brief introduction and high-level overview of offshore wind permitting, and then I'm going to discuss the Coastal Virginia Offshore Wind Commercial Project Construction Operation and Plan, and I'm just going to abbreviate that as CVOW-C. I'm going to give some specific examples about data presented in the CVOW COP, and I'm going to talk about challenges and next steps in offshore wind planning from a consultant's perspective. One thing I want to mention is the CVOW COP does cover both offshore and onshore components of an offshore wind project. I'm just going to talk about data that informs offshore development. And those components would include the wind turbine generators, the monopiles, the inter-array connection cables that connect the monopiles to the offshore substation, the offshore export cables, and the offshore trenchless installation punch-out areas. Okay, so first an introduction and a permitting overview. So as I said, we're an international consulting company, and I work with a group out of Boston, Massachusetts, but I personally work in Virginia Beach. And our group supports over, excuse me, our group supports over 25 Atlantic offshore wind development projects with multiple services. So this includes, right now, we have 7 construction and operation plan contracts, and the projects that we are doing COPs for are listed in the second set of bullet points. And you can see in the graphic, the orange polygons are lease areas that Tetra Tech has performed or is performing work in. And the leader lines, which is probably too small to see, show our clients, and the numbers relate to the different services that we provide our clients. So BOEM characterizes offshore wind permitting in 4 phases. Planning and analysis, where wind energy areas are identified, and then BOEM may write an environmental assessment for lease issuance of site assessment activities. And then during leasing, BOEM determines whether a competitive interest exists, and if a competitive interest does exist, BOEM notifies the public and developers of its intent to lease through sales notices. And the leasing stage ends when BOEM negotiates a lease. During site assessment, the leasee conducts characterization studies, and then they submit a site assessment plan, or SAP, and then if BOEM approves the SAP, the leasee assesses the site. And during construction and operation, the leasee may conduct additional site characterizations. They prepare and submit a COP to BOEM, and then if BOEM approves the COP, then the leasee builds the wind facility. So spatial data is used in all stages of the permitting process, and it increases in complexity as the process moves forward. And today I'm going to focus on the construction and operation phase. And I want to say that preparing the COP is extremely adaptive, because as we prepare the COP, we work with agencies and subject matter experts and the developer clients and the engineers. And we assess resource impacts and constraints, and sometimes that drives changes in the component design, which drives changes in the construction operation plan. So now a few details about the CVOW project and the COP. Dominion Energy is currently permitted to build a 2.6 gigawatt offshore energy project that will consist of 76 wind turbines. These turbines will be located 27 to 42 miles off the coast of Virginia Beach. And this project builds on the success of the 2 test turbines that were installed in 2020. And you can see the location of those turbines represented by the red triangles. And there's an actual picture of them as well. The planned monopiles will be located east of the pilot project, and they'll be located in a lease area that's the equivalent of 85,000 football fields. So it's a huge chunk of marine environment. Dominion Energy does estimate that this wind energy project will power up to 680,000 homes once it's built. Direct your attention to the map. The red or the orange crosses are the 176 monopiles. The green squares are 3 substations. The green lines are the offshore export cables, and the yellow polygon is the offshore export cable route corridor, where we conducted all of our survey assessments for burial of the cable route. So a quick timeline. CVOW started in 2013 when BOEM announced that Dominion Energy was the winner of the Virginia lease area. In 2017, BOEM approved the site assessment plan, and then in the fall of 2023, BOEM published the final environmental impact statement, and the joint record of decision was signed by BOEM and the National Marine Fisheries Service. In January 2024, BOEM approved the construction operation plan, and construction of the monopiles is set to begin in the next 2 weeks. It was scheduled for the beginning of last week, but they had issues with one of the support boats, and it needed to be fixed. So the boat should be on the water as early as the end of this week, and they plan to be done with building in 2026. So what is a COP? It's a detailed plan for construction and operation of wind energy. And BOEM conducts environmental and technical reviews of the COP, and it decides whether to approve with modification, or disapprove the COP. It forms the basis for the final environmental impact statement and the joint record of decision. The CVOW COP includes over 200 GIS figures and associated supporting analysis that were incorporated into 30 sections of the COP document and appendices. Now, there were 6 separate revisions that were submitted to BOEM, in which Tetra Tech team addressed comments from Dominion Energy, BOEM, NOAA, and applicable subcontractors. And the COP revisions evolved as new publicly available data was published and as survey design changed. So now I'm going to talk about, very briefly, I'm going to touch on some spatial data that was included in the biological resource and socioeconomic resource sections of the COP. We showed marine mammal and sighting data. We downloaded this from the Duke Obis CMAP portal, and we looked at 20 years, or 2002 to 2022 years of sighting. The map on the left shows marine mammal sightings, and the map on the right shows sea turtle sightings. And we just use this data to show occurrence. Like, yes, in the past 20 years, one of these was seen within the area around, and it's a very big area that we looked at, the wind energy area. So in addition to the sighting data, we also included the MGAL marine mammal density models. The map shown here is a seasonal estimated abundance of North Atlantic right whales in the study area. And this data was also used to inform mitigation measures, like a time of year restriction, where Dominion can't construct monopiles after September to April, when right whales are migrating through the area. We show shipwrecks and artificial reefs from ENC and AWA data portal. Sorry. I have to look at my notes here. We created effective fish habitat figures and calculations for all the species represented in the NIMS EFA data, and this was about 70 maps. The map on the left shows Atlantic surf clam EFH divided into adult and juvenile stages. In 2020, Dominion Energy conducted full high-resolution geophysical surveys throughout the entire export cable corridor and lease area. TerraSound used the HRG survey to conduct a seabed characterization morphology analysis, And the map on the right shows a seabed morphology analysis in the lease area. Dominion Energy also conducted a benthic characterization survey in 2020, and the survey used grab and water quality sampling as well as still and video image. And the map on the left shows a representative still photos from the survey. We also included historical survey data. For example, the map on the right shows sampling locations in BOEM 2017 habitat mapping and assessment of Northeast wind energy areas. And this data was requested directly from the agency. As part of the bat and avian section, we included the Duke marine life and data analysis abundance model for bird species. The map on the left shows an example of the MDAT model for northern gannet. During the assessment, the Biologic Research Institute conducted bat acoustic monitoring, and the results of this survey are shown on the right. So moving on to socioeconomic, obviously commercial and recreational fisheries is a huge part. We show the National Marine Fishery Management areas. We created figures using the vessel monitoring system, commercial fishing thematic maps. This data was obtained from the Northeast Data Portal and developed by NIMS. The map on the left shows the relative levels of scallop vessel activities from 2015 to 2016. Additionally, we included figures showing the community at sea vessel trip data obtained from the Marco portal. The map on the right shows charter boat relative activity from 2011 to 2015. As part of shipping and navigation section, we included fairways and shipping lanes in the U.S. Army Corps or U.S. Coast Guard port access route study. We also included figures showing AIS track densities available for marine cadastre. For example, this figure shows the relative density of commercial fishing vessels tracks transmitting AIS in 2020. So we showed marine energy and infrastructures in our COP section. We showed national maritime security uses. For example, the map on the left shows U.S. Navy danger and warning areas, as well as the VCAPE's operational areas on the right. And we obtained this data from NAFAC as part of the Navy's Common Operation Profile. So additionally, we showed marine energy infrastructure. For example, we showed existing submarine cables available in the ENC chart data. We also showed the BOEM sandbarrow areas and oil and gas draft program areas and exclusion areas. So moving on to challenges that we had and next steps. So as I mentioned earlier, Dominion signed the lease with BOEM in 2013. The project wasn't permitted until 2024. And from 2019 to 2023, there were 6 separate revisions of the COP document. The length of planning time increased complexities for COP preparation and created challenges for organization and presenting the spatial data. We had to use a strict versioning system because there were multiple iterations of design changes conducted by the engineering team. There were changes that were driven both by agency feedback regarding mitigation and constraints as well as technical considerations. And the design changes triggered edits to the GIS data and calculations, figure updates, and document revisions. The maps on the right show 3 different iterations of the lease area components. So in addition to submitting the document, we also had to include a GIS submission with every revision. And BOEM used the GIS data that we submitted to conduct environmental rules or environmental review, publish agency data on portals, and develop the final environmental impact statement. We also had to deliver data to other agencies like the U.S. Coast Guard for nautical chart updates and notice to mariners. Dominion Energy needed to show that they are using the best available data in the construction and operation plan in all sections. So as part of the revision process, Tetra Tech would work with the agency's subject matter expertise to ensure the COP spatial materials were current and relevant. So one example here is when the CVOW COP was submitted, there was no seasonal sea turtle density data. So we needed to show sea turtle occurrence in the lease area. So we used the sightings and we developed just a point count grid so we could show where sea turtles may more likely be. But since then, Newick has published the sea turtle distribution and abundance in the East Coast. So now, from now on, any environmental permitting documents that Tetra Tech creates, it will include a suite of the sea turtle maps. Given that offshore wind permitting is data-driven and adaptive, we found that web-based GIS tools are a good solution to share data in real time, both internally with our clients and with the agencies. For example, for the CBOW project, we developed agency-facing applications that BOEM reviewers can view components, constraints, and products developed using the HRG survey data. And these are screenshots of the effective or fish habitat assessment web application and the CVOW compliance mapper. So my last slide, the graphic on the right shows BOEM's renewable energy leasing schedule timeline. And as you can see, we're going to have new lease areas opening up, including the Central Atlantic, the Pacific Ocean, and the Gulf of Mexico. So as offshore wind development moves forward, I feel as a community, we need to continue to facilitate stakeholder collaboration. We need to monitor for environmental impacts during and after construction of offshore wind facilities. We need to standardize permitting requirements and document templates across multiple projects. We need to standardize and leverage site assessment data collected by the developers and incorporate lessons learned during permitting for future projects. And lastly, we should continue to fund research that aids spatial planning, especially in the new lease areas like the Central Atlantic, the Pacific, and the Gulf of Mexico. Thank you.
Thank you, Gwen. That was a great run through all of the data that are used in construction operations plans, and I want to note something for discussion later, which is that a lot of those data are available through the Marco portal, but there's one category that is not, and I want to talk about it, which is the seafloor data that the developers are really funding themselves. Next up, James Kim from Rutgers.
All right. So hello, everyone. My name is James Kim. I'm a research project assistant at RU Cool, which is located at Rutgers University. And I'm here to talk to you today about one of the projects that goes on at RU Cool in collaboration with New Jersey's Board of Public Utilities and their Clean Energy Project, which is essentially trying to model the wind environment off of New Jersey with the goal to aid offshore wind development. And briefly, before I go on, I just want to say that RU Cool is a multidisciplinary group of a lot of different professions, and we specialize in oceanographic research, and we also specialize or emphasize a lot on education and outreach. So you can see that Josh and Mike are both involved in this project, and Mike definitely highlighted a lot of the projects that go on at RU Cool. So be sure to connect with us. All right, so I'll be introducing you to the model and the data set involved. This data set, I'm going to be going through a lot of information, try to go quick. But the main thing I want you to take away from this is that this model data set is available for you, and that we are here to help you access this data set as well as understand it. So before we jump in, I'd like to briefly explain how weather models work and what WRF is. So weather models basically simulate the Earth's atmosphere to predict weather using mathematical equations. And these predictions are based on observational data, such as from satellites, airplanes, and things like buoys. We use a model called WRF, and this is developed by NCAR. And the reason we use it is mainly because it is a global use community model, basically a framework for individuals to go in and modify for their own initiatives. And that's exactly what we've done, is we've created a regional adaptation of WRF geared towards forecasting and analyzing the atmospheric environment centered over New Jersey. And so some crucial concepts to understand about the data set and modeling in general. So high resolution models provide detailed data over small areas, so very crucial for short-term forecasting and resolving local weather phenomena, while low resolution models basically give you the big picture. And those images are just there as a visual aid. So model output data is output in time increments, usually about an hour, and across a horizontal grid. So for example, if you have a 2-kilometer grid, that means every 2 kilometers there will be a data point, and if you have a 24-hour forecast, there will be a data point for each hour out to that 24 hours. And this data extends throughout the atmospheric column, so you have multiple horizontal grids extending to the upper atmosphere, so you can get a good, in order to model the entire atmosphere. So the project itself, so again, this project has been collaboration with the New Jersey Board of Public Utilities with the goal to enhance offshore wind energy strategies and maximize value for NJ ratepayers. And basically, we like to say the wind resource because wind equals power at the end of the day. And of course, we've been supported by them since April 2011. So this has been a very long project. So some key components about this project, the engagement portion, which is to identify the necessities of stakeholders and utilize our observations and modeling to hopefully quench those necessities and actually provide a planning resource for these developers and stakeholders. And using that, the things we gather from observation and modeling to perform scientific analysis to improve our understanding of the environment offshore New Jersey. So some key things about our model that make it unique. We have a model resolution of 9, 3, and 1 kilometers. We use a high resolution custom SST, or sea surface temperature, that we put into the model. And what this does is it allows us to account for essential ocean features such as upwelling and atmospheric structures such as sea breeze, which are actually unique to the New Jersey coastal environment. And in doing so, throughout this whole project, we have created this comprehensive data set that is available for a wide range of atmospheric research that extends beyond offshore wind. And prior to the development of this data set, we have our configuration was assessed and optimized by the National Renewable Energy Laboratory in 2019. And we've also done our own due diligence in validating our model to ensure accuracy in simulating the wind resource off of coastal New Jersey. So again, on the topic of offshore wind, we have produced 4 years of 3-kilometer model simulations from 2018 to 2023, which is that middle 3-kilometer grid you see there. And it is centered over those areas with, and it includes those NJ lease areas, which you can see. And another appeal of our model is we output data at high resolutions, 3 and 1 kilometers, so we can actually resolve a lot of the things that go on around, say, a offshore wind turbine. So we output lots of data between those layers of the windswept area of a turbine. So when I mentioned we use a high-resolution SST, it is for a good reason. So the Mid-Atlantic Ocean experiences the largest seasonal temperature gradients, temperature changes in the world. And it's important that we capture these changes, as well as some of the more local and local changes and events that happen on smaller timescales. Okay. So just to reiterate, the Mid-Atlantic Ocean experiences the largest seasonal temperature changes in the world, and there are also certain events that happen in our region that are that happen on quicker timescales that it's important that we resolve. And one of these is called coastal upwelling, which you may be familiar with, which happens when you, primarily during the summer, have southwest winds, and they blow along the coast displacing water at the surface, and this causes cold water from down below to come up. And again, this happens on very quick timescales that often models often overlook. As you can see there on the calendar, are 3 separate years for when upwelling events have occurred. And since the ocean has such a profound impact on the atmosphere and local winds, you can see that the upwelling extends into those NJ lease areas. So it's important that we understand this phenomena moving forward. And this is a comparison between the SST image that we use and ingest into our model in comparison to the typical SST image you see at national models. And you can see that our model definitely resolves or detects that upwelling signal, and the national models do not. But this is not to say that national models are bad. It's just that is not their focus, while ours is to effectively model this area in particular. So going to a little bit, since RU-WRF is a weather model, we are making a prediction or forecast into the future. So we want to ensure that our forecasts are reliable and accurate. So what we did is, for that 4-year data set, we took a number of wind profiling buoys off of coastal New Jersey, and we compared our model performance versus the actual observations, as well as compared to some other models, some national products, such as HER, GFS, NAM, and et cetera. And of course, the goal is to ensure that our 4-year output accurately represents the coastal NJ wind conditions, and this also increases the credibility and reliability for offshore wind stakeholders. So I'm not going to go too into depth on this. There's a lot to unpack here, but basically the main idea is that HER is regarded as one of the most accurate weather models out there in terms of short-term forecasting. And it is a constantly evolving national product. So we compared our performance of RU-WRF to it, and what we concluded was that that our model demonstrates accurate and consistent results and is comparable to models such as HER, especially in the context of offshore wind. And this is great because we can use our model to serve as a baseline to explore the sensitivity of wind in relation to local ocean and atmospheric phenomena. And again, what sets our model apart is we have the freedom to use it as a tool and basically run it at our leisure, and also share the data that we produce from it. So again, just to reiterate, this whole project has been to support the BPU and ratepayers and wind energy stakeholders in the NJ region. And in doing so, we have created this massive 4-year, 3-kilometer 3D hourly data set. So hourly data all the way from December 2018 to March 2023 for that whole 3-kilometer model grid. And this data has been validated. But again, we want to emphasize that this data is not exclusive to the offshore wind space, and it is available for the public to, and it is applicable to lots of different areas in atmospheric and oceanic research. So since this is a Marco conference, we'd like to celebrate something Marco related, which happened recently. So RU-WRF was recently integrated, or the data was integrated into the Marco portal. So as you can see here, we have monthly average wind speeds that are available for you to go and look at. And we also have plans for you to, plans to incorporate additional things like this. A huge shout out to Marco, as well as on our side, Lori Garzio, and on the Marco side, John Bogner, for doing some serious computer wizardry to get this done. So thank you. So how do you access this model data? So the raw model data, which is very useful, could be an amazing tool for researchers and students, is available on our thread server. And it includes 3-kilometer and 9-kilometer process data levels. And this is hourly output from December 2018 to March of 2023. And this output is in its format and includes variables such as wind speed, direction, temperature, and et cetera, at multiple levels in the atmosphere for that whole entire time period. So these images represent some of the things you can do with this data. These are Python plots. So one of those plots is a spatial plot of wind speed, and another of temperature. You can do wind profiles and things like that. This data is very complicated to work with. So again, we have some Python tutorials to help you with that. Or we have our services as well if you would like to reach out and contact us to help you access and understand this data set. So aside from the 3-kilometer data set, we have the pre-developed products that we've developed with the target being offshore wind developers. So let's take an example location. Let's say OCS-A 000. So what we've did is basically taken a point, and at that point extracted data from those 4 years and performed a series of analyses for wind patterns and such at 160 meters, which is the hub height of a 15 megawatt wind turbine. So I want to save room for questions, so I'm going to briefly just breeze through these, just so you can see some examples. So you can see things like box plots of wind, which is binned by season over the years, and you can look at these and really see some trends in the wind over those 4 years. We have the same for power. And these are my favorite. These are wind roses, which basically show you the magnitude of the wind as well as the predominant wind direction during the different seasons. And you can see in summer, you can see those prominent southwesterlies, which is kind of cool. So yeah, this is just the surface. And again, all these products will be available to you. So before I end, I want to touch a little bit on some additional things we do with our model to support the BPU. And this includes utilizing our 1-kilometer model grid to look at things like wake modeling, producing power estimates, and what these effects are on the power grid. So what we actually do is we can put theoretical turbines into our model to simulate these things. And this 1-kilometer data set is also available to you on our thread server, but it is highly experimental, so we recommend going with our 3-kilometer data set first. All right, so there's our software team. Basically, to see all this data, it's all in one place. You can go to our website, just type in "Are you cool?" in Google, and it should be the first thing that pops up. And you can navigate to our data section where you can basically navigate to our data section and go to our modeling page where you can see a brief overview of some of the things I discussed today, as well as all the links to the data that's available. And there's our contact. We have Mike Crowley, who is our offshore wind lead. And for all data inquiries and questions about the data itself, you can email offshorewind at marine.rutgers.edu, and we can help you access this data set, as well as explain what some of these things are. So, thank you.
Thank you, James. What do I have for time? We're at lunch. It's lunchtime.
It's almost, but
Okay.
let's take 10 minutes.
We'll give you 10 minutes.
Oh, are you all okay with that? Okay. Well, I'm going to start by just letting James know that James is relatively new to Rutgers, and Mike and Josh called me yesterday and said, halfway through his presentation, make it go off. See how he handles it. Okay, since we have limited time here, I'm going to go right to audience questions, if there are any. I can start it up if you want, but I know that you all probably have better questions than I do, so I can hear you.
This is a question for Mike directly, and I was wondering, with the proposed budget cuts for the IU system, what are there any updates, and how is that going to affect data availability and data collection?
Yeah, so the president's budget came out with a 77% cut for IUS, which basically ends IUS if that were to come to fruition. So we're doing a lot of Hill visits, the Senate and the House. We have been, we'll continue to. And we're hopeful that we will get continued at least the same amount of funding that we've been getting. But that's a big focus across IUS, not just Americas. I mean, we're all working on that feverishly.
And then, I'm sorry, I had a follow-up question for you. For the oceans map data downloads, how historic or what's the timeline for legacy data?
That's right. I'm sorry I didn't mention that. It depends on the data set. Some go back decades, others go back a handful of years. Models depends on. It all depends on the different data set. I can't give you more specifics than that, but yes, you can go back in time. You can go through any of the data sets I looked at. You can go back a year and see what the model showed, what the SSTs were, what the buoys were, any of that data.
Great. Thank you so much.
Yeah, hi, I'm Hannah Cooper. I'm with Maryland Sea Grant. I also had a question about the oceans map for Mike. Do you have any guides or tutorials for folks on how to use the tool?
That's that's a beautiful question because we just finished a bunch of tutorials that are online that you can click on. Happy to show you those at the booth, but yes, there are tutorials that Kelly Nee and her team at RPS, and I think Mary was involved as well, have put together to give quick few minutes. Here's how to do this. Here's how to do this, and it's a very complex system. There is a lot of information in there, and you can get lost real fast.
Awesome, thank you.
Hi, Mary Kemp. I'm from the Wildlife Conservation Society. I'm just curious, and with the COPs, given the fact that many of the species that we're concerned about are migratory, moving across jurisdictions and wind lease areas, how do you have to address the issue of cumulative impacts from that in any particular COP?
I don't think I'm qualified to address that because my role in the COP production is primarily a GIS analyst. So I look at the existing data and create applications and figures and analysis that go into the COP. The cumulative impact sections of the COP, which are addressed, are written by subject matter experts in the Tetra Tech team. But if you do want to read the CVAL COP or any other offshore wind permitting document, you can access them on the BOEM website. It's great nighttime reading material.
That was a good answer to a question you didn't want to answer. I'm going to ask you another one that you don't want to answer. The seafloor data. Well, this is less of a question, actually. It's more of a plug for tomorrow. There will be a presentation tomorrow. RWSC, I think someone asked about data sharing earlier. Seafloor data is an area where there's a lot of data collection going on from a lot of different places, and there's frankly not great places to put it. So we're going to fix that, and working through the regulatory process for the right time for seafloor data to be shared has been a part of that for several years. The seafloor geomorphology data set that I guess another consultant provided to CVAL, if it's in a construction and operations plan already, that's available for sharing, I assume.
So
And I know you're not speaking for CVAL.
yeah, so the data does exist,
Yeah.
and with CVAL, the data was delivered to Tetra Tech and to BOEM on hard drive. It's a huge amount of data. The smallest data set that exists is the processed bathymetry, which is at 0.5 meter resolution and covers the whole export cable corridor and the lease area. So BOEM does have the CVAL data. In September 2022, BOEM issued standardization for geotechnical and geophysical survey data. So every time a COP is published, all the data going into the COP has to be transmitted to BOEM. There wasn't a lot of detailed requirements. They did require all of the data to be put into an Esri Geo database, which involved some back and forth on what that actually meant. But the processed data, as well as simplified bathymetry data does get submitted to BOEM. So I think across all the projects and subcontractors, the data will be standardized moving forward, which means it could be digestible and shared.
Thank you.
Thank you. Colleen Brest from New Jersey DEP Marine Resources Administration. And this question's for Dr. Kim. I'm really interested in this great weather data that you're getting from offshore and how useful that would be to mariners, particularly commercial and recreational fishers who are out there. Are you aware of any efforts to communicate those weather data better with people who are actually in the field using, on vessels?
Okay, so before I answer that question, or actually, Mike, I think you would have a better grasp on this than I do, but I'm not a doctor. I graduated college about 1.5 years ago, so if you couldn't tell. But Mike, do you have anything?
So the data sets aren't currently being used by anyone offshore. In fact, we stopped running the real-time model about 1 year ago and focused on the archive data set to look at long-term trends and what was going on in averages and do studies on sea breeze, what was happening, what's going to happen with the power resource, especially in those coastal wind lease areas, how sea breezes are going to affect things, how all sorts of different dynamics, storms, what's going to happen during storms, power law, when they have to shut down turbines when storms come through versus, we're doing all sorts of different event analysis. But there is no, right now we're not running the real-time model for offshore wind at this point. That's true. That's true. You never know.
Yeah, and also I think this is a good time to clarify that the database we have was generated from when we did run the model operationally, and we don't store the full forecast. For example, we produced a 5-day forecast and a 3-day forecast during those times, but we store what we call our best forecast, which is the first 24 hours, which we believe, or which is the closest to reality. Obviously, it isn't, but that is considered our best data sets when we're using it for wind analyses and offshore to aid offshore wind development.
James, from now on, when somebody addresses you as doctor, don't clarify it. Take it from Dr. Cleary over there.
Yeah, I think my question's for James too. I'm Nicole. I'm a student at Columbia and a fellow for MACAN. Super interesting work from all of you guys. Just could you tell us a little bit more about what are the next steps for the model? Is there more of a push for reducing uncertainty or extending that time series for the available product?
So currently, I think one of our big goals is to actually engagement, which is to get this data source in the hands of actual developers or actually get feedback from those developers. Because I'm sure they also have their own models and things that they use, but and even if they do, this is a great resource for them to compare our model to theirs and also learn some things. But in the future, we are always looking for opportunities to enhance and validate our model. Specifically, NREL, the National Renewable Energy Laboratory, has released a huge WRF data set. I think it's about 20 years of data, and it kind of bleeds into the time period for when we have RU WRF. So we will work to, incorporate validation studies using both that model and our model and make some comparisons. But in terms of validation, it's kind of hard because there aren't a lot of resources out there, such as the buoys we were talking about. That's kind of all we've had recently to check or validate our model, aside from buoys that I think are deployed by actual developers that we don't have access to.